In this video, we're going to continue our discussion of thermodynamics by looking at equilibrium constants now. In the previous video, we talked about how free energy is related to enthalpy and entropy. Well, another way we can think about free energy is in terms of the concentrations of reactants and products of a chemical reaction. And we call this term KEQ, the equilibrium constant. So for a generic reaction of A moles of A plus B moles of B, your reactants, going to C moles of C plus D moles of D, your products, KQ is simply the concentration of products divided by the concentration of reactants. And you notice that for the products and reactants, we raise our concentration to their number of moles in the reaction, their molecular coefficient, stoichiometry coefficient. So, for example, if little c here was 2, we would square the concentration of C. And when we talk about free energy in KEQ, free energy, or the change in free energy, equals the change of standard free energy plus RT natural log of our KEQ. R is our gas constant and T is our temperature in Kelvin. And delta G naught, we call that a circle or naught, is what we call standard free energy, or delta G naught is standard free energy change. And really, standard free energy just means the free energy change under certain conditions. So for biochemistry, we define our standard state, which is delta G naught prime, biochemistry gets this prime here, as temperature of 25 degrees Celsius, pressure 1 atmosphere, pH of 7, all concentrations are 1 molar except water. Water is 55.5 molar. So if we look at this equation and we say our reaction's at equilibrium, therefore delta G equals 0, then delta G naught equals minus RT ln of KEQ. And this K, or KEQ, the only thing that changes the value of K is temperature. K is a constant for every reaction, and at different temperatures, it has different values. And we can look at this through what's called a Hoff Plot. So if we are doing an experiment and we're measuring KEQ in this experiment, we can plot the natural log of KEQ over 1 divided by T, where T is in Kelvin again. And with this, we can find out our thermodynamic properties of entropy, here delta S, and enthalpy, delta H. Because the Van Hoff equation says natural log of KQ equals negative delta H over R, which is our slope, multiplied by 1 over T plus delta S naught over R, which is our y-intercept. So the Van Hoff equation is y equals mx plus b. And so this is how you actually figure out these thermodynamic constants of H and S experimentally. You measure KQ at different temperatures and you make a Van Hoff plot. Now, since this is biochemistry, we need to talk about thermodynamics in terms of life. And like I said in earlier videos, life is constantly fighting against disorder. And we are ordered systems. And the way we do that is that we make our surroundings disordered. The easiest way we do that is food. We take food, we eat it, therefore making that food disordered. By taking the ordered food and making it disordered, we can use that energy to make our own bodies ordered. And we are not at equilibrium, but we're in a steady state. That means that the concentration of the things inside our cells don't really change at all. They're at a constant level, and this is called homeostasis. A good example is blood glucose level. And we are constantly giving off energy, and we're giving off substances to the environment. So we're an open system. As shown here, we're giving off water and carbon dioxide, which is taken up by plants, which can convert energy into carbohydrates, which we eat. So that's matter. We are constantly losing heat. Heat is constantly given to plants, so that's energy. So life is the definition of an open system. And for the thermodynamics inside of a cell, normally chemistry happens so slow that life isn't really feasible. So to make life possible, we have things that can speed up chemical reactions. The general term for a substance that speeds up a chemical reaction is called a catalyst. And inside a cell or a living organism, we call those catalysts enzymes. They're biomolecule catalysts. And they speed up these reactions. Now, they're usually proteins, but not always. A good example are ribosomes. They're called ribozymes. And generally, each catalyst or each enzyme only catalyzes one reaction. There are examples of enzymes catalyzing more than one reaction, but generally they only do one reaction. And this selectivity is very crucial because if you take biochemistry 2, we'll see how all the enzymes in your body are basically connected to each other to form this huge giant web of life, which I'm showing basically here, how we can take energy and then we convert that to do work, and this is all powered by enzymes. And the way an enzyme works is that it lowers an activation barrier. An activation barrier is the amount of energy you have to put in for a reaction to happen. The higher the barrier, the harder it is for a reaction to happen, and so the slower your chemistry will take. So blue line here is uncatalyzed. And the energy of the activation barrier, we call that delta G double dagger. That's what this double dagger is. A catalyzed reaction, all it simply does is that it lowers this activation barrier. It lowers this double dagger. Importantly, the catalyst does not change the overall free energy of a reaction. So you see, for both the blue and red lines for the reactants and the products, the free energy is the same. A catalyst does not change the overall free energy of a reaction. It just changes the free energy of this activation barrier. And that is it for this video. I will see you in the next video.